Okay, hello, welcome back to another lesson. And we are talking about forms of energy. Forms of energy. Last time we talked about energy. What is energy? Energy is like a currency. We talked about how energy is falls under one of two categories. It's either mechanical energy, which is movement energy, or potential energy, which is stored energy. I know we said that stored energy can either be elastic potential energy or it can be gravitational potential energy. We also mentioned how kinetic energy is movement energy, while gravitational potential energy relies on height. Okay, and there are a few other things that we talked about as well. If you're interested, you can watch that video. Today we're talking about forms of energy, and we're going to be answering this question here. How can you find an object's mechanical energy? And what are the other forms of energy? Okay, let's start by going through the motions. So we're going to start by reading through this, answering the questions, and going through it. Inshallah, this lesson should not be too long. My Planet Diary, posted by Loren, and she is in Carlisle, I believe that's how that's pronounced, Massachusetts. The first hurricane that I ever saw was a big one. The storm had weakened by the time it arrived in Massachusetts, but the wind was still so powerful it easily flung around our lawn chairs. The trees bent and swayed in the wind. When it was over, the branches were scattered across our lawn. The wind even ripped up a tree, blocking our road. The storm did a lot of damage, but we were lucky to be safe inside while watching this awesome force of nature. Okay. Let's have a look. Write your answer to the question. What is some evidence that the storm Loren described had energy? Well, let's have a look. Energy is the ability to do work. Energy is the ability to do work. Remember that? Energy, ability to do work. Bit of a French accent there. Ability to do work, that's what energy is. And of course, energy is in joules. That is the unit for energy, and it's the same for work. So that is something off the get-go, just a bit of revision there. What is the evidence that there was a lot of energy in that wind? Well, it did a lot of work. What kind of work? It ripped trees, it ripped trees, carried chairs, and probably damaged some houses. So all of that is doing work, not necessarily good work, but it did a lot of work, right? Which means it had a lot of energy. If you can't do a lot of work unless you have a lot of energy, you can't have a lot of energy unless you're able to do a lot of work. They are the same, one and the same. Okay, so how can you find an object's mechanical energy? What is this business here, mechanical energy? Mechanical energy. We know about mechanics. What is mechanical energy? Well, mechanical energy is basically just a combination of kinetic energy and gravitational potential energy. That's all it is. Kinetic energy, movement energy, and gravitational potential energy make up mechanical energy. And now you know. Let's keep going anyway. Calculating mechanical energy. How do we calculate mechanical energy? So basically, every object around you, in your house, in your classroom, in your room, has mechanical energy, which is a combination. I don't want you to confuse it. Mechanical energy is not kinetic energy. It is not gravitational potential energy. It is both. Now, sometimes it can just be one or the other, but it's a combination of both. Now, what does that mean? Let me tell you. Let's say, for example, we have a cup sitting on a table. Now, this cup is not moving. Okay, the cup is not moving, and it's got water inside it. It's not moving. So does it have kinetic energy? No. Kinetic energy equals 0. Does it have gravitational potential energy? Yes, it does, because gravitational potential energy has to do with mass, gravitational pull, and height, which is weight times height. and it's got a lot of that. So we can say, for example, that let's say it's got 50 joules, right? Now, the mechanical energy in this case, mechanical energy, or, you know what, I'm just going to write it the way I've been writing it. Energy mech, which means energy mechanical, is going to be equal to energy kinetic plus energy gravitational potential, which is going to be equal to 0 plus 50, which is 50, obviously. So in this case, the mechanical energy is equal to the gravitational potential energy, right? But it's not always the case. But I just wanted to let you that mechanical energy is both. It's always both. So you add both together. That's what mechanical energy is. And what tends to happen is, since energy cannot be created or destroyed, it can only be transferred from one form to another. What tends to happen is if one increases, the other one decreases. Now we'll look at that in just a minute. But basically, the total mechanical energy, even though it stays the same, the gravitational potential energy and the kinetic energy might change. Now let's see what that looks like in actual life. Oops, what's happening here? Why did you do that? Why did you do that? Why did you do that? Here we go. So let's have a look. Calculating mechanical energy. An object's mechanical energy is a combination of its potential energy and its kinetic energy. A combination of this and this. For example, the basketball in figure 1 has both potential energy and kinetic energy, both of them. The higher the basketball moves, the greater its potential energy is going to be. The faster the basketball moves, the greater its kinetic energy is going to be. Now this makes sense. Of course, potential energy has to do with height. Gravitational potential energy has to do with height. The higher you are, the more gravitational potential energy you have. But then at the same time, the faster you move, the greater kinetic energy you have. And so, for this basketball, for example, at point A, it has a lot of kinetic energy and it has quite a bit of potential energy. But at point B, it has so much more potential energy than it has kinetic energy. Why is that? Because it's a lot higher. It's a lot higher. Okay? So that's what we're talking about here. Mechanical energy is a combination of both potential energy and kinetic energy. Okay? Sometimes an object's mechanical energy is its kinetic energy. As we said, if the object is moving, for example, and doesn't have any potential energy, or is moving on the floor, on the ground, then obviously it's going to be mostly mechanical, or sorry, most of the mechanical energy is going to be kinetic energy. If the object, however, is just sitting high up on top of a shelf and it's not moving at all, then it's going to have a lot of gravitational potential energy, and that is going to be the sole contributor to its mechanical energy. So its mechanical energy in that case, if it's not moving, is going to be equivalent to its gravitational potential energy. Okay? So that's it. That's all you have to remember, is that mechanical energy is equivalent to both kinetic and gravitational potential combined together. So a car moving along a flat road has kinetic energy only, while a trophy resting on a shelf has gravitational potential energy only, but both have mechanical energy. So let's have a look over here. They want us to calculate the results. So this person here is shooting over at this stage. So what is the mechanical energy? The mechanical energy, remember, is a combination of both potential and kinetic. So it's going to be 22 joules. 12 plus 10 is 22. Now let's look over on this side. What's the mechanical energy at this point? It's going to be 20 plus 2, so it's also 22. So what's the difference then? The difference is the individual energies. Look at the gravitational potential. Here it's 20. Here it's 12. Here it's 12. While over here at point B, it is 20. Why is that? Because obviously over here it's higher. At point B, the ball is a lot higher than at point A, which means it's going to have more gravitational potential energy and less kinetic energy. That's all that is. Let's answer this question here. Draw conclusions. Why does the ball's gravitational potential energy increase from point A to point B? Why, I wonder? I'm going to give you a second to think about it. The answer is over here. The answer is because at point B, sometimes I write the words before I say them. It is higher. It is higher up. And remember, Gravitational potential energy is equivalent to gravitational potential energy is equivalent to mass times gravity times height, also known as weight times height, because these two equal weight. So we've got more height, we've got more gravitational potential energy. I hope that makes sense. Let's move on. Mechanical energy and work. Now remember, work is the ability to do, work and energy are the same. Energy is the ability to do work, while work is related to energy. Work is power times time. Work is energy. An object with mechanical energy can do work on another object. In fact, you can think of mechanical energy like all forms of energy as the ability to do work. For example, a basketball does work on the net as it falls through the hoop. The net moves as a result. The more mechanical energy an object has, the more work it can do. Yes, of course, the more energy an object has, the more work it can do. We already covered this. More energy, more work, more energy. So let's have a look at these questions now. The bowling ball does work on the pins when it hits them. Why is the bowling ball able to do work? Why is the bowling ball able to do work? Because it has a lot of energy. The ball is moving, so it has mechanical energy. It has lots of mechanical energy. The ball has lots of mechanical energy. Now, it doesn't have to be lots, but it does have mechanical energy. Might be running out of space soon. I hope you can read that. That says the ball has lots of mechanical energy. That's how it's able to do work. In order to do work, you need energy. Next, question 2. Let's see. How should you throw the ball to maximize the amount of work it does on the pins? Okay. Of course, remember, mechanical energy, E mechanical, energy mechanical is equivalent to E kinetic energy, as well as E gravitational potential. So how should you throw the ball? Remember, kinetic energy, E kinetic, is equivalent to half mv squared. Do you see this guy here? Velocity. If I throw it with higher velocity, it's going to have higher kinetic energy. And if it has higher kinetic energy, it's going to have higher mechanical energy. And if it has higher mechanical energy, it can do more work. So if I want to maximize the amount of work, I need more energy. And in order to have more energy, I need to have more energy, more passion. More energy, more velocity. I need to have more speed. More speed. So I need to throw the ball forcefully. I need to throw the ball with more speed, accurately at the pins. More speed. That's the key there. Okay, here's a challenge. In the type of bowling shown in the photo, the ball has a mass of 7 kilograms. So this is just standard bowling. Whilst in candlepin bowling, the ball has a mass of 1 kilogram. Does the ball with the greater mass always have greater mechanical energy? Interesting question. Does it? Of course not. How come? Let me give you a quick example. So here we have a bowling ball, a standard one, and this has a mass of 7 kg. Well, here we have a candlepin bowling ball, and it has a weight of 1 kilogram. If this one here is traveling at a speed of 2 meters per second, and this one here is traveling at a speed of 2 meters per second, then obviously the kinetic energy they both have is going to be as such, half mv squared, which is equal to half times 7 multiplied by 2 squared, 3.5 multiplied by 4, which is equal to 14 joules. Over here we have half mv squared once again, which is equal to half multiplied by 1, multiplied by 2 squared, and that is equal to 2 joules. Now, obviously, you can see that the bigger ball does have more energy. But what about if this ball is now traveling at a speed of 6 meters per second as opposed to 2 meters per second? Is it going to have more energy than the big ball, or is the big ball always going to have more energy? I think some of you have already figured out the answer. If it's traveling faster, it's probably going to have more energy at some stage. So let's have a look. 6 squared, what's going to happen now? Half of 36 is going to be 18 joules. And suddenly, the smaller ball has more energy. So back to the question, does the big ball always have to have greater mechanical energy? No, the small ball can be traveling faster. The small ball can have more by traveling faster. Sorry about my handwriting, but I'll just explain what I wrote there. I said the small ball can have more energy by traveling faster. Let me repeat that. No, the small ball can have more by traveling faster. Of course, because I just showed you that over here. Next, define mechanical energy is the form of energy associated with what, and what. So mechanical energy is a form of energy associated with motion, the speed of an object, the movement, I should say. Position, as in height, as in gravitational potential energy. Remember, it relies on height. So it could be motion, which is kinetic energy. Could be position, as in potential energy, gravitational potential energy. But remember also that we have elastic potential energy and has to do with shape. So it could be motion, which is got to do with the speed at which object is moving. Could be, or the velocity, to be more accurate. Could also have to do with position of the object, as in the case of gravitational potential energy, the height where it is, if it's falling from the first floor or the third floor or the 10th floor. Or it could do with the shape of the object, as in the case of a spring. If you're pushing a spring and then you release it, it releases the energy. Let's calculate B. Calculate. At a certain point, the kinetic energy of a falling apple is 5.2 and its potential energy is 3.5. What is the mechanical energy? Remember, mechanical energy is a combination of both mechanical energy, E mech equals EK plus EGP. So E mechanical is equivalent to E potential, gravitational potential plus E kinetic. So it's going to just simply be 5.2 plus 3.5, which is equal to 8.7 joules. And finally, if an object's mechanical energy is equal to its potential energy, how much kinetic energy does it have? If the object's mechanical energy, this guy here, is equivalent to its potential energy, how much of this is it going to have? Zero. Okay, it's like saying 5 equals plus 5. So what's that going to be? Of course, it's going to be 0 if these two are equal. If this is equal to this, which is what it's saying. So 0. Explain. Well, if both of them are equal, then it's going to be 0. That's what I will explain. No, well, we'll explain it properly. E mech equals E kinetic plus E gravitational potential. If E mech equals E gravitational potential, then E kinetic energy is equal to big fat 0. Oh, I get it. Now I know you can find an object's mechanical energy by. Everybody should be able to answer this question by adding what and what? By adding the gravitational potential energy and the kinetic energy. Great. Can we just go back for the last point? That's it there, by adding both gravitational potential energy and kinetic energy. Let's go to the next one. What are some other forms of energy? And there are quite a few of them, and they're quite interesting. Other forms of energy include, first one, my favorite one, nuclear energy. Let's just read through this first. So far, you read about energy that involves the motion, position, shape of an object, but an object can have other forms of kinetic and potential energy. These are the forms associated with particles that make up objects. These particles are far too small to see with the naked eye. Forms of energy associated with particles of objects include nuclear energy, thermal energy, electrical energy, electromagnetic energy, and chemical energy. There's quite a lot of energies, and there's more energies as well. But we'll talk about the ones that are over here at the moment. Nuclear energy, all objects. Can I just look at my highlighted notes? Okay. All objects are made up of particles called atoms. Now, we've covered this in term one. Remember, atoms, they have a nucleus on the inside. In the nucleus, we have protons and neutrons. Protons are positive, neutrons are neutral. On the outside, we have electrons that whiz around. Well, they don't really, but let's just pretend they do. And then, yeah, so with nuclear energy, all objects are made up of particles called atoms. The region in the center of an atom is called the nucleus. The type of potential energy called nuclear energy, and that is stored energy called nuclear energy, is stored in the nucleus of an atom. Can I just grab the highlighter because I'll be highlighting soon. Nuclear energy is released during nuclear reaction. One kind of nuclear reaction known as nuclear fission occurs when a nucleus splits. You see that? When a nucleus splits. A nuclear power plant, like the one shown in figure 2, uses fission reactions to produce electricity. Another kind of reaction known as fusion occurs when two nuclei fuse together or join together. Now, this type of stuff happens on the sun, releasing huge amounts of energy. Only a tiny portion of this energy reaches the Earth as heat and light. Yeah, so basically what we've achieved here on Earth, when you hear about nuclear power, nuclear bombs, nuclear explosions, that's all nuclear fission, splitting of the atom, which releases a lot of energy. However, if you would like to release a lot more energy than that is when you need nuclear fusion. Okay, and so let's continue. Nuclear fusion reactions occur constantly in the sun, as we have said. Compare and contrast. Use the Venn diagram to compare and contrast the nuclear fission and nuclear fusion reactions. So, nuclear fission, as the name suggests, fission means division, splitting. So, nuclear fission, energy is released, energy released when atom splits. Oh, come on. No, nope, splits. What about fusion? Energy. I have to write really small, otherwise it'll start moving to the next slide. Released when atoms, mostly nuclei we're concerned with, join together. And finally, both of them release a lot of energy, and they're concerned with energy stored in the nucleus. So they both release a lot of energy, and this happens on the sun. Can I just say this happens on the sun? Release. I can't. I'm so sorry, but the screen is tiny and my hands are fat. Release energy from the nuclei. Nuclei. Okay, I think that's okay. Perfect. Let's go next. Thermal energy. That is another fancy word for heat energy. Thermal energy is heat energy. Heat. Okay. Oh, come on. Okay, so thermal energy's got to do with heat energy. The particles that make up objects are constantly in motion. This means that they have kinetic energy. These particles are arranged in specific ways in different objects, so they also have potential energy. The total kinetic and potential energy of the particles in an object is called thermal energy. Okay, so thermal energy falls under kinetic as well as potential. Interesting. But it's about movement of particles. Basically, those little tiny particles that you think are not moving. So let's say, for example, the desk that's sitting in front of you right now, it looks like it's still, it looks like it's not moving, but it's made of these little tiny particles called atoms. Those atoms are vibrating all the time. When you increase the heat, the vibration increases. When you increase the energy, the vibration increases. That increases the heat. It's kind of like you eat, you gain weight, and then, no, what's a better analogy? You don't exercise, so you get unhealthy, and you get unhealthy, so you don't exercise. Yeah, a bit like that. Okay, does that make sense? So basically, you get energy, you start vibrating, you heat up, and you heat up, you gain energy, and you start vibrating. Both of them lead to each other. The higher the temperature of an object, the more thermal energy it has. And so, for example, suppose you heat a pot of water. Can I just highlight that part here first? The higher, the more thermal energy it has. So, for example, suppose you heat a pot of water. As heat is applied to the water, the particles in the water move faster on average. The faster particles move, the greater their kinetic energy is going to be, and the higher the temperature. Therefore, a pot of water at 75 degrees, for example, has more thermal energy than a pot of water at 30 degrees Celsius. That's all you need to know as far as thermal energy is concerned. It is mechanical energy. It is about movement of particles. The faster the particles move, the more heat they're going to produce. Let's talk about electrical energy. When you receive a shock from a metal doorknob, you experience electrical energy. The energy of electrical charges, I just realized something. Oh boy, this is not 4.1. Oops. I'm going to magically fix the banner on top. Look at that, magic, fixed. So it is forms of energy we're talking about. Unfortunately, for the first part of the video, it's going to say unit 4.1. Oh well, that's okay. Let's talk about electrical energy. When you receive a shock from a metal doorknob, you experience electrical energy. The energy of electric charges is electrical energy. So that is from electrons, basically. Depending on whether the charges are moving or stored, electrical energy can be a form of kinetic or potential energy. Lightning is a form of electrical energy. You rely on electrical energy from batteries or electrical lines to run devices such as computers, handheld devices, and digital audio players. Let me just explain something real quick, and I'm not going to spend a lot of time on this because I've explained it in the classroom, but I'm going to talk about it briefly now as well. So basically, electrical energy can be either static electricity or moving electricity. So electricity can either be static, which means it is not moving, and it can either be moving. If it's moving, it's a form of electricity, form of energy that falls under kinetic. If it's static, static electricity is when electrons are not moving, and it's a buildup of charge, and that's what can give you a shock if you touch a door handle or if you touch a railing or something like that, some other metallic object, or not necessarily metallic either, because it's a buildup of electrons, and if you touch it and if your feet are touching the ground, the electrons are trying to escape to the ground. Now I'm not going to go into great details about this because this is something that I will teach you later on when you're grade 11 or grade 12, but for now I'll just briefly explain it. Electrons are all around us. Sometimes devices will have extra charges of electrons. You see, electrons come in through the wall, through the live wire, and then leave through the neutral wire. However, sometimes there are some rogue electrons that don't go through the wires, and they build up on the device itself. If the device is small enough, you won't feel the shock, which is why small devices have two pins that go into the wall. However, if the device is big and expensive, Then we have 3 pins. The reason why we have a third pin, that pin is called ground. And basically it's connected to the body of the device. Why? Because in the case if there is any rogue electrons, they will go through the ground wire. What does that mean? It means you don't get shocked. Why wouldn't I get shocked? Remember, electrons are trying to escape and they're trying to go to the ground. At this stage, someone might ask, why are they trying to go to the ground? No idea. Okay, they just do. Okay, it's just one of the laws of the universe. They want to go to the ground. They want to be grounded. There's a sea of electrons on the ground, on the surface of the Earth. So that's what the electrons want to do. They want to go to the ground. They want to go to the Earth. I guess it's got to do with gravity. Probably electromagnetic. It's got to do with electromagnetic fields, I'm sure. But anyway, they want to go to the ground. And basically, the reason they shock you is because they use you to escape to the ground. If you're not wearing rubber boots to insulate you from the ground, if you are connected to the ground, remember you're 75% water. You are conductive as a human being. Humans are conductive. So basically electricity will try and escape through you, and that's how you get electrocuted. What do electricians do? They wear thick boots or thick slippers which prevent them from getting electrocuted because then they're not connected to the ground. Or they wear thick gloves which prevents them from being connected to the ground directly. So that's basically what static electricity is. It's a buildup of electrons that really want to go to the ground, that really want to go home, and then you come along and you touch the door handle and they fly through your hand, down your arms, into your body, down your feet, into the ground, and away they go home to their family. Anyway, I just wanted to explain that briefly. So that is what static electricity is. Moving electricity is just the normal electricity that goes through the wires. Okay? Let's look at this question over here. Circle 3 objects, describe 2 forms of energy each object has. I'm going to circle the cake to begin with. Cake has chemical energy, cake, and I'm just going to write, it has chemical potential energy. So that's potential energy in the form of chemical energy. So I'm just going to write E-chem. Plus it has light energy as well, which is a form of electromagnetic energy, but we'll come to that in a minute. We have a cup of coffee here, coffee, and the cup of coffee has gravitational potential energy. How do I know that? Well, if the person lets go of it, it's going to fall, which means it has a gravitational potential energy. It also has thermal energy. And we've got the light bulb, which has heat as well as light. We've got the person, which has kinetic energy as she's moving, as well as gravitational potential energy, as well as chemical energy stored in fat. So we've got quite a few different energies here. I'll let you. We've got the plane, which has kinetic energy, as well as gravitational potential energy. And there's plenty of examples here. Electromagnetic energy, so that's got to do with light. The light you see in one of the is one type of electromagnetic energy. Yes, electromagnetic energy. Electromagnetic spectrum is massive. So it's got to do with microwaves, radio waves, X-rays. I've gone from one side to the other. Visible light, and so on. Infrared, ultraviolet, all of those are examples of electromagnetic energy, and all of those are carried in light energy that comes from the sun. Okay, so let's read through the paragraph. The light you see is one type of electromagnetic energy. Electromagnetic energy is a form of energy that travels through space in waves. The source of these waves is vibrating electric charges. These waves do not require a medium, so they can travel through a vacuum. That's why they travel through space or empty space. This is why you see them. This is why you see the sun and the stars, because you're actually looking at, those images wouldn't be traveling to you in the form of light. The microwaves you use to cook your food and the X-rays doctors use to examine patients are also types of electromagnetic energy. Other forms of electromagnetic energy include ultraviolet, which means above violet, and infrared, which means below red. You see, we see from red to violet. That's what we see. Red, orange, yellow, green, blue, purple, violet, if you can call it that. What about anything above violet? Ultraviolet simply means above violet. What about anything below red? We can't see it. It's called infrared. Yeah. We've got radio waves and cell phones use, receive, da, da, da. So all of that, that's another form of energy. That's light energy. Okay, so all of that, basically light. And they travel in waves. 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 They have a wavelength. They have troughs and peaks and crests, and there's the amplitude on the side and the wavelength on the side, y and the x-axis. So yeah, that's what the waves look like. Like a sine wave or a cos wave, or sorry, or even a tan wave. You can have a tan wave. Different waves, different waves. That's the point. You can have different waves. Okay, chemical energy is the type of energy that's found in food. Chemical energy is in the food you eat. In the matches you use to light a candle. The candle itself, the wax, has chemical energy as well. And even in the cells in your body, chemical energy is potential energy stored in chemical bonds. When you break those bonds, the energy is released. Often when these bonds are broken, the stored energy is released. For example, let's highlight that part, that's very important. Chemical bonds. For example, bonds are broken in your cells and release energy for your body to use. But it's not just for your body. For example, in the car. So in the car, we've got chemical energy. The car, your car, will run off potential energy. Well, if you have an electrical car, which quite a few people do now, that will run off stored electrical energy. So that's potential energy. But if you've got a combustion car, just like a normal petrol car or diesel car, then that runs off chemical energy because there is energy in the bonds stored in the gasoline, and when you break those bonds, you release a lot of energy. So that's another form of chemical energy. Petrol, diesel, kerosene, all of those are chemical energy. Okay, let's answer question one. Why do the particles of objects have both kinetic and potential energy? Okay. Why? Look at my notes. They're constantly in motion, so they have kinetic energy, and the particles also have potential energy as a result of their specific arrangements in the objects and the fact that they have bonds between them. So, two types of energy: kinetic energy because of their movement. Okay, they have kinetic energy because of the movement, and they have potential energy or stored energy because of the bonds and their arrangement. Because remember, potential energy has to do with position, shape, and chemical potential energy has to do with bonds. So now you've got three potential energies. Gravitational potential energy has to do with the height, which is position. Elastic potential energy has to do with the shape, when you stretch or compress a spring or a trampoline or any object, or even a ball, like a bouncy ball. If you compress it, it acts as a spring. And then you've got the chemical potential energy, which has got to do with bonds, covalent, and what's the other one? Covalent and ionic. Of course, ionic being between metals and nonmetals, while covalent between non-metal and non-metal. Excuse me while I mute my notifications over here because it is getting annoying. Excuse me. Thank you very much. Let's look at the next one. The next one says, the energy you get from eating peanut butter and jelly sandwich is in what form? It is a form of chemical energy. Okay. Oh, I get it. Now I know the forms of energy associated with particles or objects include kinetic energy and potential. Oh, they want us to list all of them. Nuclear, thermal, electrical, electromagnetic, and chemical. Oh, okay, right, okay. Nuclear, chemical. I'm not doing them in order. I'm being a rebel. Electromagnetic, which is light. What else did we talk about? Electrical, and thermal. How could I forget thermal? Heat. Yeah, that's great. Let's do the quick summary. Write the letter of the correct answer on the line on the left. Okay, let's do that. I'll give you a chance to go through it. To find an object's mechanical energy, you add what? You add the potential energy and the kinetic energy, obviously. So what I would like you to do is I would like you to pause the video, do it yourself, and then check your answer with me, okay? A form of energy not associated with the particles of the object is what? A form of energy not associated with the particles of the object is mechanical energy. So that one is not associated with the particles. This one is made up of kinetic energy and gravitational potential energy. So that is different. Nuclear fusion occurs in the sun. D. And the total potential and kinetic energy of the object is its mechanical energy. Sorry, the total potential and kinetic energy of the particles of an object. Of the particles. Ooh, particles, they got me. Thermal. Remember, okay, so this is what we have now. I want you to pay attention to this. We have energy. Is it to do with particles or not particles? If it's got to do with not particles, then it's either going to be kinetic or gravitational potential. Could also be elastic. I'm gonna write, yeah, or could be elastic potential. So that means elastic potential. If it's got to do with particles, it's got to do with thermal, electromagnetic, which is light, electrical. Oops, no, we're not done yet. We're not done. Or maybe we are. I think my computer decided that we are. We'll see. If it works, it works. If it doesn't work, we'll call it a day and we'll stop there. Let's see if that works. Continues to work. Can I bring that back up again? No, not you. All the way down here. Is that working? I don't, oh boy. Okay. I don't know if it's going to work. I think my computer has had enough. Oh, here we go. Good. Mechanical energy is associated with the motion, position, or shape of the object? No. Okay. My computer doesn't want to do it. Have a good day. Bye-bye. I'll see you in the next one.